Welcome to our comprehensive guide on gRPC with Go. In this tutorial, we'll explore how to build high-performance remote procedure call services using Go and protocol buffers. gRPC is a modern open-source framework developed by Google that enables efficient communication between distributed systems. We'll cover everything from basic concepts to advanced streaming patterns, giving you the skills to implement robust microservices architecture. By the end of this tutorial, you'll understand how to leverage gRPC's binary serialization and HTTP/2 protocol to create lightning-fast communication between your services. gRPC stands for Google Remote Procedure Call, and it's a high-performance open-source framework that revolutionizes how distributed systems communicate. Unlike traditional REST APIs that use JSON over HTTP/1.1, gRPC uses protocol buffers for serialization and HTTP/2 for transport. This combination delivers exceptional speed and efficiency. gRPC is language agnostic, meaning you can build services in different programming languages and they can seamlessly communicate with each other. The framework provides fast and efficient communication through binary serialization, which is significantly smaller and faster to parse than JSON or XML. This makes gRPC ideal for microservices architectures where performance and cross-platform compatibility are crucial. Protocol buffers, often called protobuf, are Google's language-neutral and platform-neutral mechanism for serializing structured data. Think of protocol buffers as a more efficient alternative to JSON or XML. They define your data structure in a simple protofile using a special syntax. The key advantage is that protocol buffers generate smaller payloads, parse faster, and provide strong typing across different programming languages. In the example shown, we define a user message with 3 fields: an integer ID, a string name, and a string email. Each field has a unique number that protocol buffers use for efficient serialization. The syntax equals "proto3" specifies we're using the 3rd version of the protocol buffer language, which is the current standard. Setting up gRPC in Go involves 3 essential steps. First, you need to install the protocol buffer compiler, which converts your proto files into Go code. Next, install the Go gRPC packages that provide the runtime libraries for building gRPC services. Finally, install the protalk generator plugins that specifically generate Go code from your proto definitions. The installation process uses Go modules, so you'll run go get commands to download google.golang.org/gRPC for the core gRPC functionality, and google.golang.org/protobuf for protocol buffer support. The protalk-gen-go and protalk-gen-go-gRPC plugins are installed using Go install, which makes them available as command line tools for code generation. Defining a gRPC service is where you specify the contract between your client and server. Services contain RPC methods that define what operations clients can perform. Each RPC method specifies its input parameters and return type using protocol buffer messages. In our example, the user service defines 2 methods, getUser and createUser. The getUser method takes a getUser request message and returns a getUser response message. Similarly, createUser accepts a createUser request and returns a createUser response. This approach provides strong typing and clear contracts between services. The service definition acts as both documentation and the source of truth for what operations are available. When you compile this protofile, it generates both server and client code in Go, ensuring that both sides implement the same interface correctly. Implementing a gRPC server in Go involves creating a struct that implements the generated service interface. Your server struct must embed the unimplemented user service server, which provides default implementations for forward compatibility. Each service method receives a context and a request, then returns a response and an error. The context is crucial for handling timeouts, cancellations, and passing metadata between services. Your implementation contains the actual business logic for each RPC method. The key steps are: implement the service methods with your business logic, create a gRPC server instance, register your service with the server, and start listening on a network port. The server handles all the protocol buffer serialization and HTTP/2 communication automatically, so you can focus on your application logic. Creating a gRPC client is straightforward and involves establishing a connection to the server and using the generated client stub to make RPC calls. First, you create a connection using gRPC.dial, specifying the server address and connection options. For development, you might use gRPC. With insecure to skip TLS encryption, but production systems should always use secure connections. Once connected, you create a client instance using the generated new user service client function. This client provides methods that correspond to your service definition. Making RPC calls is as simple as calling methods on the client object. The client handles all the protocol buffer serialization, network communication, and deserialization of responses. Remember to properly handle errors and close connections when done to avoid resource leaks. gRPC streaming enables real-time, continuous data exchange between clients and servers, going beyond simple request-response patterns. There are 3 types of streaming. Server streaming allows the server to send multiple responses to a single client request, perfect for scenarios like fetching large datasets or live updates. Client streaming lets the client send multiple requests while the server responds once, useful for uploading files or batch operations. Bidirectional streaming enables both client and server to send multiple messages simultaneously, ideal for chat applications or real-time collaboration tools. In the proto definition, you use the stream keyword before message types to indicate streaming. This creates entirely different method signatures in your generated code, with special stream objects for sending and receiving messages over time. gRPC delivers exceptional performance through several key technologies. HTTP/2 provides multiplexing, allowing multiple requests over a single connection, header compression to reduce overhead, and server push capabilities. Binary serialization with protocol buffers creates much smaller payloads compared to JSON and parses significantly faster. Connection pooling allows reusing connections for multiple requests, reducing the overhead of establishing new connections. For best practices, always implement proper error handling using gRPC status codes and descriptive error messages. Use context throughout your application for cancellation and timeouts, ensuring your services can handle network issues gracefully. Properly manage connections by closing them when done and implementing retry logic for transient failures. These practices ensure your gRPC services are robust, efficient, and production-ready. We've covered the essential foundations of gRPC with Go, starting with understanding gRPC fundamentals and protocol buffers for efficient data serialization. We explored how to define services and implement both server and client components. We also discussed streaming patterns that enable real-time communication and performance optimizations that make gRPC so powerful. Now, you're ready for the next phase of your gRPC journey. Build a complete gRPC microservice that incorporates all these concepts. Implement authentication and security features to protect your services in production environments. Add monitoring and observability to track performance and diagnose issues. Finally, deploy your services to a production environment where you can see gRPC's performance benefits in action. With these skills, you're equipped to build high-performance distributed systems that can scale and communicate efficiently.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.